let's get on with tunneling today. Well, we've been dealing with several properties uh, that quantum mechanics claims they've observed, whatever observed means. Does observed mean with two eyes, like observed, like I observed the girl who was taking off her clothes? No, nothing like that. Okay. No, when they say observe, they mean they infer. But they say observe so that people listen, observe, they say, oh, they saw it with their two eyes. And so if they saw it with their two eyes, who's going to deny it? Here you have all the so-called scientists, and they say, we observed. You're going to question that? I mean, you're going to say you need to go to the lab, and when all these people are telling you the same thing, that they observed something in the lab? But it turns out that the so-called observation is not an observation. It's not with the two eyes. What they observed was the visible things. What they touched was the tangible things. Okay, and tangible things are typically not anything atom or below. It's usually atom or above. And atom, that's a question also. Okay, they touch many atoms. You know, I can touch a chair, which is gazillions of atoms, yeah, but I can't touch one atom, or I wouldn't know if I did. And so you got to keep that in mind. These people use the word observe, and that's why I hate the word observe in science. It shouldn't be there. First, because we don't do observations, and second, because we cannot observe that which is intangible and invisible. Mother Nature's mediators for gravity, magnetism, workings of the atom, light, etc. They're all invisible and intangible. So we're not going to detect them through a lab experiment, and we haven't in the last 10,000 years. No one has been able to determine what Mother Nature uses because it's invisible and intangible, and you're not going to figure out by running an experiment. You can run all the experiments you want. You won't be able to touch or see that which is invisible and intangible. And so the only way to look at this is step back and find out how Mother Nature could be doing this magic trick. And I give the example always, you see this guy going like this, and a box goes up. Okay? And it turns out, the box is attached to the rope. Rope is attached around the pulley, and the guy's pulling on a pulley, on the rope through the pulley. But the question is, if you didn't see the rope, and the guy was doing this, and the box goes up, are you going to say it's just black magic? Or are you going to assume that there is something that you simply can't see, that the guy is pulling on? And that's the same situation here. We can't see light. Does that mean there is no mediator for light because you can't see or touch it? You put your laser and you put your hand right through it. And you're not hitting atoms or anything, you're not hitting the things that, colliding against the thing that makes up light. Your hand goes right through that. Does that mean there's nothing there? There's no physical object there? Okay? And so the question is, if it's intangible and invisible, of course you're going to run your hand right through the laser beam, whatever entity is there, and you're going to say there's nothing there because I can't see or touch it. And so you got a problem because Mother Nature has made specifically that mediator invisible and intangible. And until you get that through your thick skull, you're going to be running around in circles and running experiments and saying, oh, I'm going to run another experiment, see if I can detect it. You'll never be able to detect it. There's only one way, and that's sitting back and visualizing how Mother Nature could be doing all these things with some object which is invisible and intangible. So again, what quantum mechanics does is they found all these properties, all these phenomena, and what they do is describe the phenomena they observed or did not observe, and they have no idea what is mediating that phenomena. That's where we're at today. Okay, that's what quantum mechanics and essentially all of mathematical physics is all about. And so here's the recap that of what I've been talking about lately, and that's these properties that quantum supposedly discovered. Okay, these are things that they saw observed in the lab. What did they observe? Well, they say they observed decoherence. Well, what do we mean by that? Did they see an object do what is known as decoherence, which is a phenomena, a process, a verb? Have they found the noun that does decoherence? Have they found the mechanism, how Mother Nature does this magic trick? And the answer is absolutely not. They have not. So here's a decoherence. I call it incoherence. Okay, and you see the slit experiment, and they say that this particle, because they do everything, they simulate everything with particles, says the particle goes through both slits. And why is that the case? Well, they say if the slits weren't there, there would be coherence between these two. Essentially, they show them as particles, but they're going to turn them into waves. They're going to say that these two waves are in phase. But it's because something gets in the way and they interact with their environment that it becomes incoherent. In other words, it's coherent until it interacts with the environment. That's what these people are saying. Okay? And so, with that, we still don't know how Mother Nature does it. All they're saying is if there's something there and it interacts with that something, it becomes incoherent. Until then, it was coherent, but as soon as it interacts, in fact, with your vision or your touching, then it becomes incoherent. You can't predict what's going to happen, or there's interference of some kind. So so they're not telling you how it works, how the magic works. They're just saying we observed, right? Something happened, and we're going to call that decoherence, and we're going to use it for technology. We don't know what it is. We don't know how to explain it. We don't care about that. We're just going to use it because we found this effect. That's what they're saying. Entanglement, no different. What is entanglement? Well, it says that what you have. Oh, here, let me get this up here. Entanglement means that one particle here can affect another one over there without a mediator, without anything between them. Now, what sense does that make? How can a particle affect that one over there without any mediator? And they just say that it does. Okay, so it does. I'll concede, I'll grant. What is it? How does it do it? How can we make sense of that? And the answer is, it is so. That's what they say. Well, that's only a description, and we don't have an explanation. And they say, well, we can use it for technology. Again, it's all this stuff about technology, which is confused with science. Science, we have to explain how it does. How does Mother Nature does this trick? Not just describe and say it happens. Yeah, we notice that when they move this over here, that one moves over there in some certain way. Like in this case, I'm showing we have counterclockwise here and clockwise over there, and then when you turn one of them around, the other one turns around instantaneously. That's what they found. In fact, that's not what they found. What they really do is they have polarizers where they check the orientation at that location. So it's kind of like a static experiment. It's not something where you're seeing really motion at the cross section where you put the polarizer. Okay, so keep that in mind. Okay, I used an ellipsometer when I was in the semiconductor industry, and that's essentially how they do these things. They do it using an ellipsometer. Okay, next one, superposition. That's another one that I covered. Okay, what is superposition? Well, it says that while the horse gallops, it also stands still. What sense can that possibly make? How can something be standing still and moving at the same time? And they say, yeah, a particle can vibrate and not vibrate at the same time. It's excited and not excited at the same time. What sense can you make of that? Does that make any sense to you? I mean, if it does, well, maybe I'm wrong. I don't know. But I'm saying that's nonsense. It's called poppycock. It's idiocy, irrationality. Use any of those words, you're fine. Schrödinger's cat, the cat is both dead and alive. What can that possibly mean? How can a cat be both dead and alive? And what they use for that is two features. They use complementarity and uncertainty. And here you see the cat is alive and dead, both, until you open the box and you peek inside. Then it suddenly collapses to one of the two states. And again, they use all these observations, as they call them, these phenomena, superposition. They use decoherence, complementarity, uncertainty. They use all those. They mix them up, bunch them into one. They say we observed each one of these phenomena. And here's complementarity. Okay, the next one there. Niels Bohr's complementarity. What does that mean? Well, it's duality. It's something they love. They love all these dualities. Light is both a particle and a wave. That's what good old Niels says. So you see the particles that are rolling, the yellow ones, and so light is both particles and waves. Waves being a bunch of vectors only. Particles, I don't know how you can get them to move up and down because it's got to be oscillating. So we can't reconcile particles with waves, but they say light is both particles and waves. And so what sense can you make of that? Well, what does that mean? And again, they say, well, we don't understand that. We don't care because we're going to use it for technology. And as long as they find some use for the effect, they're happy because they say the rest is philosophy. We're never going to figure this out. And we can't figure it out. Why? I'll tell you why they can't figure it out. Because they're using particles. You cannot explain this with particles and with one-way mechanisms, which is, what you see there. Both waves and particles are outgoing. They allegedly come out of the atom. The atom produces the waves. The atom produces the particles, whichever or both, and shoots them outwards. Okay? And, under the rope model, it's a bidirectional mechanism. So it's a lot different than this. There is no such thing as a wave, first of all, because again, those are a bunch of vectors. That's all we're seeing, moving vectors. What is vector? Magnitude and direction. Okay, so what is that? Mathematics, that's what it is. Okay, and here you have uncertainty. Okay, showed this the other day also. Here's Mr. Heisenberg and his uncertainty principle. And what is he saying? Well, he says that, the ball bounces at the same time that it stands still. And see, they're all related, all this uncertainty, complementarity, together with decoherence and superposition. They have all these concepts all together from different angles. And they put them together to try to give you an explanation. What's the explanation? An irrationality. They give you something which is absolute nonsense, which is duality. That it has two aspects which are contradictory, which are irreconcilable. Motion and standing still, location. And that's what you have there. The ball stands still, it also moves. And so this is the uncertainty principle. If you think that's going to make your life any better, well, they say they can use it in technology. Well, we don't care if they can use it in technology if they cannot explain what's causing it, if they cannot make sense of it. And right now we have a problem because we're reaching the end of the line where, they've had this for 100 years now. Quantum's been around for 100 years, and they cannot explain any of this. And here, they're at the same starting point as they were in 1926, 1927, when they started concocting all this so-called theory of quantum mechanics. Today, we've made no progress whatsoever. They have no explanation for any of this. All they have is more equations for different aspects of this, and that's all they have. And right now, they've kind of painted themselves into a corner because they still cannot give you an explanation for this. And they've abandoned that. It's like Richard Feynman says, they've given up on that. So they don't have an explanation. He said that in 65. And here we're 40 years, 50 years down the road. They still have no explanation for this. And so what more are they going to do? You think they're going to find a solution to this? And the answer is no. And the reason they cannot find a solution is they're dealing with particles. Mother Nature cannot be using particles. This was the time to wipe the board completely clean and start all over and brainstorm some new mediators. We can't continue using particles or waves. That's the issue. And fields, it's not a physical object. Field is a mathematical concept that is of value at each point in space. That's all a so-called field is. So there is no such thing as a field. There's no such thing as a wave. And particles, right now we're not even using particles. We're not using the classical corpuscle. What we're using is zero-dimensional equations. That's what a particle is, an equation. That's all it is, a function. Okay, and spin, which we dealt with the other day, here it is. Okay, and that means that the dancer spins both ways, okay, clockwise and counterclockwise, until you, again, see or touch him. As soon as you see or touch him, he collapses to one or both, to one of the two states. Okay, meanwhile, he goes clockwise and counterclockwise. That's what they're saying spin is. And it turns out spin is not even spin. Spin is a static concept. It has to do more with orientation. But as we explained the other day, if they use the true spin, first of all, it doesn't match what they observe in the lab, in the effects they observe. And second, they cannot explain attraction with that anyways. So what if an electron spins? How does this electron from this atom over here attract that electron from that atom over there? How do you produce attraction with two little balls? Spin them any way you want them. Okay, spin the tops, one clockwise, the other one counterclockwise, spin them both clockwise, spin them both counterclockwise. It doesn't matter. One top will not attract the other top. So at some point, you got to put an elongated mediator between objects, atoms, right? In order to be able to explain how Mother Nature does her things. Then you can explain action at a distance. And the only assumption you have to make is you can't see or touch that mediator. Why? Because that's not what an object is. An object is that which has shape. Okay? So yeah, as long as you insist on see, touch, and doing experiments, then you're in trouble. You'll never answer the question. Okay, here's tunneling, which is the next phenomenon. We've seen all these other ones. This is another crazy phenomenon of quantum mechanics. Okay, and it goes more or less like this. You have a snowball, big ball, okay, and it hits this mountain and it bounces backwards. Okay, that's what we would expect for a snowball to do. Okay, it hits the mountain, bounces back. Okay, no problem there. So far, so good. Okay, what they say is, why can't that ball go up the mountain and climb over it and go to the other side? Okay, and so here let's show that. Okay, it's going to try to do that. Going to try to climb, and it doesn't have the energy, whatever that is, to reach the top and go over the side of the mountain. Okay, so what happens is they cannot explain if they were to find the snowball on the other side. That would be a miracle, right? There's no way it can happen, at least in classical mechanics. You would need so much energy to get up that mountain that's not what they observe in the lab. Okay, so what is it that they observe in the lab? Well, what they observe in the lab is this. Okay, they observe that the ball is on the other side. Okay, so now how do you explain that? Turns out this ball was rolling along. It didn't climb the mountain. It just went through it. And they call that tunneling. It's like it went through a tunnel, like if the mountain had a tunnel in between it. And so, yeah, now we have a problem because we have to explain that. What do you mean it's got a tunnel? What is that? And the way they explain it is more or less like this. So hold on to your seats right now because this is just going to drop you flat face down on the floor. Okay, here it is. What they say is the reason the snowball ends up on the other side of the mountain is it rolls and the snowball turns into a wave. It just goes as a wave through the mountain and then it arrives at the other side. Now, ain't that neat? Man, I wish I would have thought of that. That's the best explanation you can have, right? Or is it? I mean, don't you call that black magic? I mean, not even the Bible has this kind of stuff. This is really ridiculous. They're saying that the ball turns into a wave and that's how it ends up on the other side. Okay, and you say, okay, doesn't make any sense, but okay, what's the explanation for this? I mean, are they just going to say it is so? Well, more or less, that is what they say, okay? They say that the ball rolls, turns, as soon as it hits against the wall, you have this interaction, right? Kind of like the decoherent stuff that it interacts now with its environment because it hits something, and now it's going to act a little differently, okay? And so you say, well, what is the explanation for this? And here's a nice, fine young lady who explains it for us. I assume she has a degree. I haven't really looked into her past, but she has a YouTube channel. She tries to explain it, and this is what she explains, okay? And she explains that she knows nothing. That she has no clue. Okay, here it is. Her name is Jade Tan Holmes, and she's a cute little girl. Oh, that's great, but here we do science. We don't do beauty. You want to do beauty passion pageants? Well, you got to go somewhere else. So she says, it may seem stalling that we're treating the wave function exactly like an electromagnetic wave, whatever that is, because you treat a wave function as a wave, you haven't made much progress. They're both concepts. They're both verbs. A function is an equation, and a wave is an equation also. There is no such thing as a wave. Wave is a bunch of vectors that are moving somehow because they make them move in mathematical physics. And she says it's hard to imagine something so abstract like the probabilities of electron locations as a real physical thing that travels and reflects in tunnels. Yeah, it is. It doesn't strike her. I mean, it doesn't snap her out of it, that hypnotism, that something is wrong. Are we just going to accept this and bow down and say yes to the professor because he's going to be the supervisor of my thesis? The truth is, scientists still don't know exactly what a wave function is. They don't know what a wave function is. Well, I'll tell you what it is, lady. A function is an equation. That's all it is. It's a bunch of numbers or a bunch of letters that represent numbers, etc. So yeah, we do know what a wave function is. It's got nothing to do with physics. Physics deals with objects, and this is math. That's what it is. They don't know whether it's purely a mathematical tool we've created to help us predict things about quantum objects, or whether it's a real physical wave. My God, poor girl. I mean, it is a mathematical tool. Hopefully, wave function only has to do with math, but it turns out the wave also has only to do with math. There is no such thing as a physical wave because you have to identify what it is that's waving. You know, when you do the simulation in front of the class, in college, well, you take a string and you move it up and down, you know, got one here? Yeah, maybe here. Something like this, okay? I hope you can see that. It's a very thin black wire, okay? And when they do that, okay, why can you see the wave? Well, because they put a physical object, in this case, some kind of thread, some entity, elongated entity. Then you can wave it up and down and you can talk about wave because what's waving is the string, the thread, the rope, whatever you're using. But there is no such thing as a wave without a physical mediator. And she's talking about a real physical wave. Oh, what's the wave made of? What is this wave? You know, are we talking about a string, a rope? What is this wave? And she thinks it's a real physical thing. That's what she learned by rote in college in order to get her degree. And now she goes on YouTube and just peddles the same thing she memorized by heart for the test. Is this science? Or is it poetry where you just recite what you learned by rote? But what they do know, this is what they know. We know. I don't think I know. I don't think you know either. What they do know is that it can be modeled pretty much perfectly by wave mechanics. I don't care if they can be modeled by wave mechanics if that's an equation. That's what she's talking about. Again, we're missing the object. We don't know what's waving, what physical object is doing the waving. And so so she hasn't explained anything. And you wonder, why is she on YouTube? And she does a lot of videos just like so many others out there where they supposedly go in there and say, oh, I can explain how quantum works, or let me tell you a little bit about relativity or string theory. And what they do is they repeat over and over again for the last 50 years the same old stuff. She hasn't contributed anything new. And you say, Bill, aren't you being a little harsh on this girl? I mean, she's just trying to make a living, going on YouTube, etc. No, we have to embarrass these people. There's so many of them. They're crowding out the internet, they're crowding out YouTube, they're crowding out so many other platforms out there. And all they do is repeat the same thing that the other guy next door said. It used to be that we needed a teacher in every class. If these people are going to be doing teaching, on YouTube, all we need is one teacher for the entire world. Everybody can tune in to that teacher from any part of the world and learn the same thing. We don't need the same material being given by, thousands of different people. Now you might say, well, maybe I like the way this person says it instead of that one. Yeah, fine. How many versions do we have for quantum? How many versions do we have for general relativity? How many versions do we have for string theory? Do we need, let's assume we have 10 versions of quantum mechanics, different ways of explaining something. Do we need any more? We have thousands of these people on the internet. What are they there for? To say the same thing as the guy next door said, to say the same thing they all learned by rote in college without providing anything new, without giving you an explanation, instead of all they give you is a description, mathematical description said in English, in regular language, in vernacular. So they give you this presentation. They say, look, this is what the mathematicians mean. And this is how I translate it for you people who are laymen. Okay, or lazy men. And so they give you this version, and they're all giving you the same version. Maybe the guy focuses a little different than the other guy. Again, with 10 people, we should cover the whole planet. We don't need more than 10 people on YouTube explaining the same thing over and over and over again. And what we have is thousands of people because they're out of work, and they say, look, I got my degree. Should I go and look for a job at a company? No. This girl says, well, I'm kind of cute. I think I can go on the YouTube and make some money just spreading the same thing that all the other guys do. She's cuter than the gal next door. Well, maybe they'll watch her instead of watch the other lady. Is that what science is about? And this is all we have today. All we have is these people just crowding out the internet, getting thousands of votes, lots of ups. Everybody likes them, say, oh, I like it. What do they learn? They learn the same nonsense that they're going to learn from anybody else, and they all say the same exact thing. And we haven't made any inroads in 100 years. Not one of these people can explain to you, like she says right there. They don't know. They don't know. All they know is that it works, that they saw an effect, and they can use that effect because it works. They can use it in some kind of technology. And they say that's as far as we can go. And they call that science. Okay? So yeah, we don't have an explanation today for any of the things these people do. Okay, so here's the moving vectors that I was talking about. Okay, this is, let me get this one out of the way here. What you're seeing there is a moving vectors. Okay, this is what they're saying that they're seeing, or that's what they're imagining, because they don't see this. They're imagining that this is what's in that invisible world. But what are you staring at? You're staring at a bunch of vectors. What are those arrows? They're just vectors, mathematical vectors. What is that? Magnitude and direction. And you have magnitude and direction, which is moving. That's what you're staring at. So yeah, these people have no explanations for that invisible world of quantum mechanics. And the main reason for that is you cannot see or touch the mediators of gravity, of light, of magnetism. You can't see or touch them. You can only visualize them, close your eyes and try to imagine how Mother Nature could be doing this process, what the mechanism that she's using in that world. And hopefully you do it with objects, because otherwise you're introducing black magic. So you have to have an object. What is an object? Is that which you can see and touch? No, it's that which has form, which has shape. Okay, so what are my conclusions for all these effects, these quantum effects? Well, here it is. Conclusions. Quantum fails to explain the key mechanism. What are they? Decoherence is irrational. Entanglement, they cannot explain. It's irrational. Superposition, also irrational. Schrodinger's cat being dead and alive at the same time, irrational. Until you observe, until you peek inside the box. Complementarity, duality, that light is both a particle and a wave, irrational. Uncertainty, that the ball stands still at the same time it moves, and when it moves, it doesn't stand still. When it stands still, it doesn't move. Well, that's quite rational. It's just incredible that they needed an equation to explain that, which, any kindergartner could have told you. Okay? Spin, irrational. Why? Because it's not spin. And even if it were spin, you cannot explain attraction, action at a distance attraction, with two tops that are spinning. How does one top affect another top? I don't care how they're spinning. So it's irrational because the mechanism, the fact that it spins, even if it did spin, which it doesn't, but even if it did spin, you cannot produce pull, which is the only force missing in quantum mechanics. Tunneling. Tunneling is irrational. Why? Because they convert the ball into a wave. They convert the photon or the electron into a wave. They say it's got both features. It's both a particle and a wave, and they go back and forth because that's the only way they can get it through the mountain, the ball through the mountain. And no problem. I'll even concede all that. I just need the process. I need to know the mechanism by which a particle converts into a wave and a wave back to a particle when it's on the other side of the mountain. Now, how's that for an explanation? That's what we need. We need an explanation. If you don't have an explanation, then all you're doing is black magic. All you're saying is, it is so. It is so. I haven't learned anything because you're telling me that, one thing converts by magic into the other. What's different than that than saying that Jesus Christ went to heaven, came back, and then went back again, I guess, right? Back and forth. And you say, well, that's superstition. Well, what is this? What is this nonsense? Is it, what do you want to call this? Superstition? You can call it, instead of superposition, superstition is probably a better word. It's nonsense. This is poppycock. This is idiocy. And we've been living with this now for almost 100 years. Not all of them at the same time. They discovered these phenomena as time went by, but this is what we have today. This is the summary. Okay, corollary. No wonder Bohr, Heisenberg, Feynman, among others, everybody else in quantum, candidly state that no one understands quantum mechanics. No kidding.